Alright, so this is going to be a continuation of redox reaction prediction. We went over the common oxidizing agents yesterday. There's one more that I want to note here, and it's the reaction or the half reaction of hydrogen peroxide decomposing. Don't forget that hydrogen peroxide is a peroxide, so in this case oxygen gets a negative one. That leaves hydrogen with a positive one, oxidation state. And you can see right here the reaction for the oxidizing, or the reduction half reaction, is going to be forming water. There's our -2 and our +1 for hydrogen. You can see the only element changing is our -1 to -2 for our oxygen, which means is undergoing reduction. And since these are common oxidizing agents, yes, these are the ones that are reduced. So that should make sense. As you can imagine, there is the other product of oxygen produced. That is actually in our next slide, our common reducing agents with the hydrogen peroxide decomposition. We know that this is a free element, so it gets an oxidation state of 0. So we can see that yet again oxygen is undergoing an oxidation reaction. It goes from a -1 to a 0, so it has lost electrons. This is called a disproportionate redox reaction due to the fact that one element has both been oxidized and reduced in the following reaction here. Alright, this is where we stop. We need to determine or talk about the common acidic anhydrides. And anhydride just means without water, so when these are added to water, these are going to be forming acids. And so this is actually what we talked about in our synthesis reactions and back in Unit 2. I just wanted to make you aware that commonly the oxidation state, if possible, of the nonmetal will stay the same. So oxidation states will stay the same if possible. It's not always going to work out, but for example, we know that when we add carbon dioxide to water, we make carbonic acid. So let's go and try out these oxidation states. We know that oxygen is always going to be prioritized as a -2. That means carbon would have a +4 in this case. Let's go down here and look at the carbonic acid. We have a -2 and a +1 for our hydrogen and our oxygen, leaving us with the carbonate. If overall carbonate's overall charge is a -2, and we have -2 times 3, which leaves us with a -6, that leaves carbon attaining a +4, and that's great because you can see that the oxidation state between these two are the same. And this is just if possible, when you can do this is a trick on trying to help you predict which acid will form based on the common acidic anhydrides. So let's go do a couple more. So let's do nitric acid. So I want you to determine which of these will form nitric acid in water. So we have a couple of options. So let's go and label our oxidation states here. We have a +1, we have a -2 for our oxygen and hydrogen. If nitrate's overall charge is a -1, we have a -2 times 3, it's a -6. That leaves nitrogen with a +5. Take a minute and try to label the oxidation states here. Pause the video if you need to. Okay, if you paused and you try to label your oxidation states, the one I have highlighted here you'll see is a -2 and a +4. Well, that is not always going to be what's forming that's not always going to be the one that is going to be forming nitric acid. The one that actually has a common oxidation state with nitric acid is the lowest one, dinitrogen pentoxide, -2 for the oxygen and a +5 for nitrogen. So commonly, if you're going to be given this as a reactant and you're adding it to water, you'll be forming nitric acid. So these are just some tricks on helping you predict products. Don't forget though, nitric acid as a reactant will commonly form, if it's concentrated, it will form nitrogen dioxide. If it's dilute, it will form nitrogen monoxide. So this is just the opposite part of the reaction. Same thing over here. Let's label this one. We have a -2, and we have, you can see -2 times 2. That leaves chlorine with a +4. And on this lower one, we have a -2 here, leaving chlorine with a +1. So you can see these nonmetals have varying oxidation states because they are going to be forming different types of acids. And you can imagine these look like chlorate, so they're probably going to form a chlorate-related acid. So we have a couple of options here. HClO4, HClO, O3, HClO2, and HClO. Okay, so you can label the oxidation states there. Last one, our last two, excuse me, we can form phosphoric acid, phosphorus acid, those are your common ones, or sulfuric acid or sulfurous acid. Those are your other common ones. So these are just make sure you know that commonly non-metal oxides are going to be forming acids in water. Okay, this sheet you have, let me minimize here, maybe. Okay, so you have this page, and this looks like a lot of information about redox, but technically it's not all about redox. It's about stuff that we are already fully aware of because we know how to do reaction prediction for the various types of reactions. So I'm going to walk you through these types of reactions, but in the viewpoint of redox reactions to represent that every single type of reaction can be redox except for double replacement because they don't change their electrons, they just switch partners. So looking here, you'll notice that you already know what this is. We have a single replacement reaction where we have metals. Don't forget your metal activity series. The most active metals are going to be at the top of the series, and this is actually on the next slide. But the activity series will have the ones that are most active at the top, and then they'll be able to replace the ones below it. The most active, though, means, you can see here, this metal transitioning to this metal. What has happened? It's able to be oxidized because the metal has lost an electron to form a positive cation. You can see this metal cation forming this metal anion. So the free element, this metal, has to be able to replace this one that is bound up in a compound. It's just you don't see the anion here because the anion was the one that was the spectator ion. So this single replacement relates back to the activity series. The more active means that it's more easily able to be oxidized, so give up electrons. Active just means that the electrons are either loosely held and able to be given away, or they are very electronegative and they wish to have an extra electron. The key note here on this one is that copper is very low on this activity series, so it is very unreactive. And that's one thing we saw yesterday in the lab where copper did react with concentrated nitric acid forming the nitrogen dioxide. But copper in that 6 molar HNO3, we left it overnight and it wasn't very reactive. We'll see how much reacted overnight, but for the first 30 minutes of it sitting there, nothing happened. So it takes a lot to cause copper to react. The example here is zinc yields copper 2 chloride, and then, you'll see it forming zinc, chloride, and copper. When we do our NRE, our chlorines cancel out. This worked out because we had 2 being the oxidation state change of zinc and 2 being the oxidation state change of copper. You can write those out. Therefore, we needed no multipliers or coefficients. The next example is still related to activity series, but this is the hydrogen gas formation part of the activity series, so it's called hydrogen displacement. Your metal here is your solid metal, and it's reacting with an acid. You saw this whenever you had your zinc and hydrochloric acid in the lab, and this one is relating to the fact that the hydrogen gas is going to be relieved of being a bound up compound. So what's going to be replacing the hydrogen is the metal. So the metal is going to be forming a salt here, salt, because the metal cation is going to be able to get it with the X anion. And in this case, you'll see that sometimes the spectator ion will be that X, will be that anion. So looking at this reaction, you'll see zinc is your solid, HCl will be able to be separated because of its strong acid nature, and then zinc chloride will be able to be separated, 2 chlorines, and leaving us with H2 gas. H2 gas is molecular, so it's not able to be ionized, but your zinc stays because it's zinc and then zinc 2+. They're 2 totally different things. Your Cl minuses, 2 Cl minuses are able to go away, so then you're left with zinc plus 2H+, yielding zinc 2 and hydrogen gas. And if you labeled your oxidation states, you go from 0 to +2 and then +1 to 0. You can see one is oxidized and one is reduced. Yet again, for this reaction, the metals have to be fairly active to force that hydrogen out of the acidic form. Commonly, copper is not going to be that reactive. You have to have a metal that is able to give away its electrons, so one that is active like zinc is here. Okay, let's talk about oxidizing and non-oxidizing acids. These are things that have a method on how to solve these types of problems, but you have to really have a lot of practice because sometimes they're hard to predict. So read with me here. The metal is oxidized, the acid is reduced, right? So we have to be talking about acids. Well, that means we have an H plus available. Think about H plus for a second. H plus only has one way to go. It can either, well, we'll do this. It can become hydrogen gas, which has a zero oxidation state. So from a +1 to a 0, that is undergoing reduction. We know that hydrogen can be at H plus and occasionally go to a -1 for a hydride form. That is very, very rare. So that would be even more reduction. So that one's actually our less likely option in our two reductions. We do know that hydrogen, with a 1+ charge, will not go to H2+. That is impossible because hydrogen only has one electron. So you have to think about your possibilities here. It can be reduced. It's not going to be oxidized here. So that's why we have the terms oxidizing acids and non-oxidizing acids. So for example, in this case, H plus is the OA, which means it is reduced, and then there's only a couple types like that. Commonly we'll have HCl, the one that's being reduced, just like we saw in our previous example. Occasionally we'll see phosphoric acid and sulfuric acid, but it's only when it's cold and dilute. It's very specific. And the reason this happens is because the anion in the acid has no tendency to be reduced. So for example, chlorine in the HCl example, chlorine is a -1. If it lost electrons, it would form Cl to be reduced. If it gained electrons, it would form Cl2-, and we know that's totally not true. So in this case, chlorine could form, the only thing it could do is to go to the 0 state. So from a -1 to 0 would mean oxidation. So you have to have your pairings right. You have to work through and say, okay, if this is reduced, then this has to be oxidized. So the key here is the anion is the weaker oxidizing agent, so it's less likely to be reduced. And so less likely to be reduced than something like H plus, or also known as hydronium. Next, we have the oxidizing acid. So in this case, it's the anion that is going to be with the one that's more likely to be, what does OA mean? Reduced, okay? So the anion is the stronger oxidizing agent. So in this case, hydrogen, yes, or H with the 1+ oxidation state is still there, but is it the one that's going to be forming hydrogen gas? No, it will not be, okay? Something else is going to be undergoing reduction. So commonly we have our hot and bothered acids here. So we've seen this one. We haven't seen sulfuric acid too often, but it still is an option. Our best example here is our one with copper and concentrated nitric acid, forming a 0 oxidation state for copper to, in this case, a 2+. In the lab, you'll see that this forms a green-blue color. This is actually forming copper 2, which is the more blue shade. It's hard to see in the acid because the acid forces a couple of copper 1s to form as well. So it actually forms a combination, but we're focusing on the copper 2. The H plus is still an H plus. It's still a 1+ oxidation state. So you'll note that this is not an this H plus is not involved in the redox reaction whatsoever. But we talked about earlier the nitrogen here in nitric acid having a +5 oxidation state. You'll see that this is still nitrate here, so this is not the one that is the part of the redox reaction. It is the nitrogen dioxide that's involved, -2 and +2. So the two parts of this reaction would be the nitrogen and the copper. And the copper. There we go. So you would have to go through and do your balancing, but this is balanced in acid because of the fact that it's literally reacting with a very strong acid. And you can note that this nitrogen here is going to, is a 4. Ooh, what am I doing? Plus 4, so that's actually gaining